Okay, welcome back. So this is the 11th week of this series, and fourth and final week that I'll spend on neutrinos. So today we'll pursue neutrinos a little bit more. And let me comment that after this week, we're off because it's the exam schedule. You don't get any exams, though. And we begin again on February 27th for the final set of lectures. And this is the last one, as I said, on neutrinos. And then we're going to go on to finally, my talking about gravitational waves when we start again in February. And we'll end on kind of future perspectives in astronomy, cosmology, particle physics, and so forth. You'll have already had it, at least for most of particle physics and for neutrinos. And we'll do it for the others. So basically, that's the plan. And I hope to see you at the end of February for the beginning of gravitational waves, which is, of course, my favorite part of this. So let me see where we are on neutrinos, and then my plan today is to show you basically the work that's being done now and for the future, plans for the future for this field. So you can kind of I've brought you pretty much, I'm going to mention some of the things, pretty much up to date on where we stand. But now we'll talk about what people are doing to try to answer some of the big questions of the future, and I'll show you the projects around the world that are which are pretty ambitious, that are being done to move this field to the next stage. So first, let me just highlight some of the conclusions that we've made so far. So we've seen that when we did particle physics that there are these three families of particles, and we've now seen that there's also three known neutrinos, each associated with one of those families. We also learned, and I'll come to that in a minute, that it's more complicated than that because these families for the quarks and even for the electron and muon act independently. There's three families in nature. They have different masses. Their other features are the same if they're on a horizontal line, but they're essentially independent of each other, and we have, at this stage, absolutely no understanding why there's three and not one, why there's three and not five. It's just the way nature is given to us. In the case of the neutrinos, we have an added feature which I'll talk about, and that is these neutrinos are not independent of each other. So they're different from the others. That many of us believe is hopefully a clue for going beyond this so-called standard model that I described in particle physics. And when I described the standard model in particle physics, including quarks and everything else, the key word was model. Not a theory, it's a model, and that's because there's so many outstanding unanswered questions that the standard model doesn't answer. And one of the only clues that we have at the present time for how to get beyond this model, nature has to tell us how to get beyond it. We haven't been able to do it just theoretically, is the neutrinos, and especially the fact that they interact with each other and have mass. We don't know a lot about them yet, but that's outside of the standard model. It's not predicted in the standard model. Therefore, it's a place where we can get some clues beyond that. The other hope for information that we have already beyond the standard model, possibly, is the particle that's not on here, and that is the one I showed in the upper right-hand corner on a different plot, which is the one responsible for mass. That is, we've now seen that there's this so-called Higgs phenomenon that tells us how mass is generated, a theory that does that, but we know very little about in nature whether it's the simplest version of that, more complicated ones that might help us answer some of the unanswered questions. So two of the big thrusts for the future of what we've talked about so far, which is, let's say, not cosmology, but fundamental particle physics, is to get beyond where we are, is to understand the Higgs sector somehow. And people want to build new accelerators to do that. And the other is to pursue the outstanding questions in neutrinos. And I'll show you today what's being done there, and pointing out both the ambitions of some of these projects and how both impressive and complicated they are. So we draw on this that there are three neutrinos. We saw the evidence that there's three neutrinos, which is the right-hand side here. And that is that if you produce the Z particle, which is much heavier than these neutrinos, you can take all the decay possibilities for the Z particle, and from the width, which is how rapidly it will decay, you can actually determine how many neutrinos there are. And that comes out very accurately 3. So when I draw the picture of 3, it comes out very accurately 3, unless there are more neutrinos, but they have different features. And we call those sterile neutrinos. The simplest version is just a neutrino that's very heavy, too heavy for it to decay via Z. The other way is that the neutrinos are the same kind of particles, but they don't have the same interactions, and that's called sterile neutrinos. I showed you an example of actual data that we have to take seriously, but isn't confirmed, that there's evidence that maybe there is a third neutrino. Not only that, that it interacts with the present ones and creates a different kind of oscillations. And that was seen in an experiment at Los Alamos. And the experiment was done in a second generation at Fermilab. So it's serious data, but it hasn't been independently confirmed by a different group, a different technique, and so forth. And so that's a question in the future. The working assumption is that we have 3 families of neutrinos. Many theoretical ideas for how to get beyond what's limited in the standard model. People like to incorporate more neutrinos, help solve some of those problems. So there's theoretical motivation to do that. There's some experimental information, but it's not solid enough for us to declare anything now that there's neutrinos beyond. But it's one of the open questions, and one that I've put aside in everything that I did when I did the phenomenology, and that I won't talk about today, but I want to keep it in your mind. Maybe when somebody teaches this course 5 or 10 years from now, it's a real thing, or maybe not. So we've mostly talked, when I generated the features of the neutrinos, on natural sources of neutrinos, and there's lots of those. And there's lots of neutrinos. They don't interact very much, so they're hard to detect, but there's lots of neutrinos. I list here 6 different ways that a substantial number of neutrinos are made. They're made in the atmosphere by cosmic rays hitting particles in the atmosphere, making secondary particles that decay and give neutrinos. They're made in the burning of the sun, in the core of the sun, and we spent some time on that. They're developed in a burst, which has been detected. I didn't show you the data, but it has been for supernova. That's a star when it burns up all its fuel collapsing under gravity. They've been observed kind of, not very definitively, from other sources of neutrinos, other sources astrophysically, but I didn't have time to go through that in some of the work that I've done. The big impressive experiment that does that is located at the South Pole. And in the South Pole, detectors are buried deep under the ice. The ice deep down is very, very clear, clearer than the clearest water. And the ice serves as a target for neutrinos to interact. Nothing else gets that deep, and they've been able to see them and point where they come from. They're very high energy neutrinos, and there's some evidence that some sources, astrophysical sources, give neutrinos. Why do we care? We care really probably because one of the problems that I haven't talked about, but might at the very end, is that we don't know where cosmic rays come from. So cosmic rays are common, go through us all the time. They come into the atmosphere, and we don't have a good explanation for where they come from. What creates cosmic rays? Cosmic rays are made and even have energies that are much higher than we can produce on a particle accelerator. So what is the nature that makes those? There's ideas again, and there's some information, but we don't know very much. One of the reasons we don't know is that most cosmic rays, by the time they get to the Earth's atmosphere, are charged. They've gone through areas that have magnetic fields, or they've scattered off particles, so that what we measure or look at when we look at a cosmic ray isn't pointing back to where it was created. It's coming from another direction. So we don't have a very good way of pointing back. Neutrinos, in principle, give us a good way. So with neutrinos, because they don't bend and they go through and don't interact very much, give us the possibility. And that's why, even though there isn't very good information yet, seeing possible sources like GRBs or AGNs that give neutrinos are a possible way to not do what I've emphasized in these lectures, which is about neutrinos themselves and their physics, but using neutrinos as a tool to maybe understand more about the universe or the phenomenon that happen in some of the objects in the universe. There's also neutrinos that come from the early universe. We don't know how to detect those because they're so low in energy. They would be very, very interesting because we'd be able to go back to very early times if we could see the neutrinos from the early universe. But because they were made in nuclear processes, meaning starting at low energy, and because they were made when things were very dense, there's been many interactions since then, and they are what we call thermalized. That is, they've gotten down to low enough energy that they've survived, but they're such low energy, they're kind of diffuse and hard to detect. But people are trying to build possible devices that could detect neutrinos from the early universe. There's no really good idea at the present time or good project, so it's not one that I'm talking about here. Another one that is, I think, something that I won't talk about in detail, but you can kind of keep your eyes open, is we do wonder what the interior of the Earth is like. We have ideas, of course. We think there's a hot core, and we know something about the kind of materials that are in the Earth, and we have models of it. We don't have a good way to penetrate and tell what happens at the center of the Earth or in the core or what it's made out of experimentally. One possibility, and people have now been able to detect at least a few, is to detect the neutrinos that come from nuclear reactions that happen deep under the ground, and use that not to understand neutrinos again, but to understand the Earth that we live on. So there's kind of two themes to the work done with neutrinos. One is to understand neutrinos themselves, how they interact, what they are, whether there's only three, blah, blah, blah. And the second is to use neutrinos as a tool to understand astrophysics or understand the Earth or understand something else that they are very good at doing. Today, I'm going to talk some about the bottom, because as physicists or experimental physicists, when we want to try to really understand something, you want to control all the variables. If you can control everything, then you can study and understand things. When neutrinos are just given to us, like the ones listed on the top, we have some idea where they came from, what their energies might be, and so forth, but we can't control it. If we can make neutrinos ourselves and change what their energy is or where they come from or where they're going, then we've simplified the problem a lot. And we've made the transition now to being able to make neutrinos that give some of the interesting effects like neutrino oscillations with man-made sources of neutrinos. By man-made, I don't mean our bodies, that also makes neutrinos, but I mean an apparatus that makes neutrinos. And I'm going to spend most of today talking about two different types because they give neutrinos in very different energies. One is nuclear reactors, and one is particle accelerators. So I'm going to spend a lot of today talking about what kinds of projects are being done to make the next step for neutrinos, where we can study what we don't know by making them ourselves. So first, let me look at some numbers. The one that we looked at the most carefully was solar neutrinos. So there's a lot of them. So just to remind you, every second, there's 2 10 to the 38, that's a big number, solar neutrinos produced by our sun. That's the number that are produced. Almost all of them actually get out of the sun. They're not absorbed in the sun because neutrinos don't interact very much. So almost all of them get out of the sun. They're traveling at about the speed, nearly the speed of light, but the sun is far enough away that every neutrino that we detect from the sun has taken 8 minutes to get from the sun to us at the speed of light, which is the speed of neutrinos as well. By the time they get to the Earth, there's 70 billion neutrinos every second in 1 centimeter patch. So in your fingernail, basically, or your finger, there's something like 70 billion neutrinos every second that's going through you. Luckily, most of them don't interact, so we don't pay very much attention to them, but that's how many there are. And the idea that I talked about was to see those neutrinos to study the interior of the sun. And we talked some about that in the last lectures. And using those experiments, I showed you an experiment done in Japan with a huge vat of the purest water that we've been able to make. And with that, they've been impressively able to image the sun, look at the sky, but then see the sun and its size from not photons, which we're used to using to see the sun, but from neutrinos. And that was one of the most remarkable experiments done in the last decades. And it was given a Nobel Prize, as I pointed out. Then people started studying neutrinos from the sun, and to me, this is a perfect lesson of why physics is a combination of theory and experiment. So we have a very good theory for how the sun burns, and it has to do with fusion. Fusion is the theory. We know what the materials are in the sun. We know pretty much what the age of the sun is, so we know the materials. And from that, we can calculate in detail the nuclear reactions that happen in what we believe is the process that makes the sun burn. That process is called fusion. And in that process, neutrinos come out at different energies. The one that's most prolific happens in what's called the PP reaction. That's shown here. And so this is decades because it's a log scale. This is energy going quite low, but from 0.1 to 10 MeV. And the dominant one that's tallest on here is the PP reaction, but then we have these other reactions. And experiments were done over the last decades that were able to look at these, or these, or these, and they all had a common feature, that the number of neutrinos, neutrinos were seen in each of them, like they should have been, so there was no puzzle that way, but the number that were seen was 30 to 50% of the number that you calculated. And for me, it's then an example of why it's important to, no matter how much you think you might know something, like you think you know the sun burns, and people saw neutrinos from the sun and basically gave them a prize for doing that. But then doing the experiment better, we found a puzzle. That puzzle we couldn't even explain, and there were big debates. Somehow there's less neutrinos from the sun than we expected. That might mean that this model that we think is so good by calculating how the sun burns and gives the right heat and temperature and neutrinos at different types that are seen here is wrong. And the number of neutrinos that come are an indicator that it's wrong. Or alternately, that from the sun, when the sun burns and creates these neutrinos, there was a possibility proposed actually for a different reason years ago by Bruno Pontecorvo, that maybe the neutrinos actually do something rather exotic, which is in passing from the sun to us, change their identity. And that was the second possibility. This was debated for several decades until experiments were good enough to resolve that. And I showed you those experiments. And finally, the clincher in this were two experiments. The labels on them were the word snow and the word Super Kamiokande. Super Kamiokande is the one that I showed you in Japan. That's this huge, huge vat of water. And it measures neutrinos from the sun directly of a certain type, electron neutrinos. But the combination to be able to see all the reactions that happen were complemented by an experiment in Canada called SNOW, Solar Neutrino Observatory it means. But of course it also sounds cold, which it is in Northern Ontario. And the combination of the two solved the problem. And that solved the problem of what happens, not the physics. And that is, this is kind of the fact that earlier experiments saw only 1/3 or 1/2 of what they should. What was missing were reactions that are called neutral currents that give a different reaction. And when that was done in the combination of the experiment in Canada and the one that was done in Japan, the final answers come out exactly as the prediction. So where we stand now is the explanation for how the sun burns is perfectly fine. We even have a good source now of neutrinos from the sun. But we now have a new phenomenon, and a kind of exotic one, and that is that we're forced to believe that neutrinos in passage in their 8 minutes from the sun to us actually change identity. Strange phenomenon. If you let them go far enough, they change identity back. And that is a phenomenon that mathematically I showed you that we call neutrino oscillations. That these neutrinos, the three types, are not independent of each other, and they kind of change identities from one to another as they pass our given time. A rather exotic statement. And as I said, that's not predicted by this great theory that I talked about, our model, called the Standard Model. It means we know from doing the phenomenology that they have some mass. And that's what I'll mainly talk about today, which creates certain possibilities. Everything that I'll talk about is not a theory. It's how we understand the neutrino oscillations phenomenologically, what actually happens, and can we consistently draw a story of what happens when they change from one to another. That doesn't give you the underlying reasons why that happens. So this, to me, is one of our only big clues in how to get from what's called the Standard Model that I showed you so carefully to some real theory of particle physics. And hopefully that'll happen in the future. With this phenomenology, and I showed you the identity changing, there's some key parameters that can give us clues into what we don't know. And that's the goals of the future experiments that I'll show you. And there's a couple key parameters, and I'll mention what they are. So in concluding what we do know, and that is the neutrinos change identity, we indicate that by graph that I show here. This is mass going this way, and we have three kinds of neutrinos, what we call the mu, the electron, and the tau neutrino. But if we look at mass instead, We have 3 mass states also, but they're not the same as the 3 states that have the quantum numbers that make them in one family or another. In fact, they're funny mixtures. If we take the data as best we can, I summarize all the things that give the data here, but I won't go through that. Then we know that the lightest one is dominantly this neutrino, but partially the other 2. And the next one is here, and the next one is here, and there are these mixtures of the neutrinos. This comes not from anything theoretically, but just looking at the data in all these different experiments that I showed you, putting it together in a consistent way. So I list what those experiments are here, so anyone who really cares can see where it came from. But that's the status of where we are. What we don't know here, I pointed out, is that I've only shown you one possible picture. There's actually 2 pictures that are consistent with the data, where a different neutrino is the bottom state. We don't know which neutrino is the lightest at this point and which one isn't. And that's part of what we want to resolve as we go forward. So we have mass. The neutrinos have mass. A little bit of mass. It's small compared to the other particles that we have. But one thing that we don't know is what is the mass. We don't know which one is the lightest, as I said. But we also don't know whether the lightest one has mass, and if it has mass, how much mass. We just know mass differences from the 2 mass differences that I showed you. In other words, when I showed the picture here, we don't know whether this is 0 or offset, and we just know the mass differences from here to here and here to here with some errors from the experiments that were done. So one big question, and it matters in terms of how you want to interpret it later, is what is the mass of this lightest one? Since we know, once we know that, then we know the mass of the next ones by the mass difference, with the ambiguity that we're not sure of 2 solutions that I talked about. So how do we then tell the mass of the lightest one? Next, I'm going to show you how that's being attacked. People have tried to do that, but so far we haven't seen a mass, only a limit on the mass. How can we get the mass of the neutrino? The best way is to go back to the original way neutrinos were discovered. That is, you might remember that neutrinos were discovered because we found that in radioactive decay, in beta decay, instead of the charged particles coming out with a unique energy, there was a distribution for this electron, for the electron that came out in what's called beta decay, rather than it coming out a unique energy. That's because the neutrino carried some of the energy away. So we saw a shape like this, and if we knew what we were doing, we could have put a limit on the neutrino mass from that. I'll show that to you in a few minutes. But now we want to take this and somehow from the data of this beta decay, determine what the neutrino mass is. What affects the neutrino mass is that it changes what the highest energy you can have for the electron. If some energy goes away in mass for the neutrino, the electron can't get to as high an energy as it could have otherwise. And so what we want to do is look at this very end and see how far it goes. And that's the scheme that's used to determine the energy, the mass of the lightest neutrino. And there's a big new project that I'm going to show you that's intent on doing that. And we have reasonable hope that it'll get to a place where you can determine the mass. And I'll show you that. In order to do this, when I show it to you, there's some criteria. First, we need to make, in order to see the ones out here, I'll give you the numbers in a minute, we have to have lots and lots of neutrinos because they're somewhere, only a few of them end up here. You'll see how many. So we need a very strong source to make this decay. What's shown here is tritium, the decay of tritium. Secondly, in order to see the ones here, we can't confuse what the energy is. So we have to determine the energy very accurately so that we don't call one that landed here just because of experimental errors one that's out here. We have to be able to draw this shape very accurately. We need good energy resolution. We need to have an endpoint energy for the neutrino that's well determined, a small endpoint energy. We need to take a lot of data. What that means is we need something that's going to be stable for a long time, because you want to compare data over a long time. Usually with an instrument, not too hard to make an instrument that works okay for an hour or a day or maybe a month, but to have data that you take for a long time requires a lot of work and expertise to make sure that things don't drift with time. And lastly, you want it to be clean and not be encompassed by a lot of backgrounds. So the experiment that I'll talk about is in Germany, and it's called KATRIN, and it is looking at the endpoint of tritium or some other heavier elements. This just shows the picture that if you have hydrogen-3 or tritium, when it decays, it makes helium-3 and an electron or positron and a neutrino. So what was seen when we introduced the field of neutrinos was that people expected there to just be these two, no neutrino, and the electron would come out with unique energy. When it instead came out with a spectrum, Pauli made the statement that maybe there's a missing particle. That was the neutrino. That's the old history. Now we're going to follow that up by actually going back and doing that measurement to high precision for the very highest energy ones. This shows the best result presently on measuring the mass of the neutrino. And what we get is that the neutrino mass, the electron neutrino, which we think is the lightest one, but maybe not, is 2.3 eV over c squared. When I show you later, you'll see this is a little big for determining the lightest one. We expect for other reasons it to be lighter than that. So the best present limit is interesting in that it sets a limit of 2.3 electron volts, but it's not low enough, as I'll show you. This is the experiment called KATRIN, and for size, I think there's some humans more or less shown in here, in the little picture. You can see this thing is pretty big. And there's a long distance then coming to it, this human size. So this is the size of a football field or something in total length. There's a whole bunch of steps to get to how it works. I won't do them in detail, but just give you a sketch. First, you have to have a source that does the beta decay, and will give neutrinos as one of its outputs. So it makes the source that they have it gives electrons from beta decay 10 to the 10th every second. So there's 10 to the 10th, that's shown here. 10 to the 10th electrons every second coming out from beta decay. But now we have to do something with it. So we have to focus it and do something with it. So the next stage is to capture those electrons and get them pointed toward an apparatus that will be able to tell what its actual energy is, so we can look at the final endpoint. That's shown here. So that happens in this part. Then we have what they call a pre-spectrometer. That means a spectrometer tells the difference in energy. So it's a quick way of telling the energies. They do that so that they can just pick out the ones that are near that endpoint and run it into this more final apparatus that will be able to do the very accurate measurement. So in that way, they reject the low energy electrons and they guide the electrons into this bigger apparatus. And then in the bigger apparatus, they measure very carefully the energies. It's at high vacuum, shown here. And out the very end is only 1 electron per second. So they start over here with 10 to the 10th electrons per second. But by the time you get here, and what we'll see in data, once they do it, it's something like 1 electron per second. So that's the scheme. And there's a final detector that sees that one electron that comes out. So that's the scheme. This is a picture of it, arriving at a small town called Leopoldshausen in Germany. The picture makes it look worse than it is because they picked an angle where it looks like it's crushing all the houses, but it actually is quite big going through. So you can see the apparatus. This is then calibrating it well, so you know the energy accurately that you measure when you measure something that's 17 eV, you know the energy very well, and so this is just the kind of thing that people do to do that. And finally, there's some details of kind of which states they look at, but now you want to measure this very, very accurately and pick on the ones that are near the endpoint. So they have ways to extract just those. This is just the details that they use. A molecular tritium source for technical reasons, which I won't go through, instead of just atomic tritium. And that is a detail experimentally. This is the history of the measurement of the neutrino mass. So this is what we knew. I'll remind you that neutrinos were discovered here. So when they were discovered, if we actually cared about the neutrino mass, we knew that it was less than a few hundred eV already, just from the data that caused us to predict that there are neutrinos. So basically the fact that something, go on. So the fact that we found neutrinos by the fact that you saw the beta decay spectrum was here, and the accuracy of those experiments were enough already to see that the neutrino was less than 1,000 eV, meaning it was less than an MeV, but it was a limit of a few hundred eV. And through the next 30 or 40 years, different experiments have brought it down to a present limit that I showed you earlier is of the order of 2 eV. That's not good enough, and then they're doing this experiment. We don't have a result yet, but it should bring the limit or the measurement down in this limit level here. So we should be down where we should be able to see it. Do we think that's good enough? Probably or possibly, and we know that by indirectly knowing what limits where the neutrino mass will be. The upper bound on it, there's an upper bound on it that comes from measurements in cosmology, looking at the certain line, Lyman alpha line in astronomy, tells you that the mass has to be less than where the present limits are, which are up here somewhere. And you also know a lower bound, which comes from some of the other experiments. At least it's consistent with the lower bound. So we expect the limit to the mass to be somewhere in here, and this experiment will bring us down pretty much close to this line. So we're cautiously optimistic that this experiment in the next few years will actually determine the mass of the lowest neutrino. Then we'll know the masses of the others by the mass difference. We still won't know which is the lightest neutrino. That has to be done in a different way, and I'll address that as this lecture proceeds. Okay. Next, I want to talk about reactor neutrinos. I started by saying we want to produce, so that's all I'll say about telling the mass of the neutrino. And we should be able to do that. To understand more about the phenomenon of neutrino oscillations, we have two man-made ways to make neutrinos where we can study them, control them, and study them in detail. The first, as I mentioned earlier, is nuclear reactors. The second will be particle accelerators. Nuclear reactors, I show the key ones here that have been used and are being used to look at neutrinos coming out of a reactor. I'll also show you why they complement each other, what you do on accelerators compared to what happens on reactors. Reactors give much lower energy neutrinos. The key ones in the world that have given us and are giving us information on reactor neutrinos rather than just neutrinos from the sun are one called Double Choose that's in France. That's shown up here. And it's a double reactor. One called Daya Bay here, which is 4 reactors together near, not in China, but near Hong Kong, in a bay that's near there called Daya Bay. That's the most impressive one. I'll spend most of my time talking about that one. One in Korea called Reno, here. And there are no major problems or disputes between them. They kind of, so far, confirm each other, with the Chinese one being the most accurate. So that's where we are. And now let's talk about what happens in reactors and what you can do. So in a reactor, you start out with uranium, and you have the nuclear fission reaction, and from that, you can create energy, which is what a fission reactor does. I'm not going to go through the physics of a reactor because I don't have time, but you get about 200 MeV for each fission, and in that there's something like a half a dozen, 6 neutrinos that come out for each fission that happens. And you have lots of fissions in a reactor. So the reactor, typical reactor that maybe is 6 gigawatts is what they measure it, but a commercial reactor gives a huge number of neutrinos, something like 10 to the 20th turn out to be anti-neutrino electrons per second. So there's a huge number of neutrinos that come out, but as I keep saying, it takes a lot of neutrinos to be able to see anything because most of them don't interact. You need a lot of material to make them interact. So this is the process, and there's different neutrino reactors around the world. Typically, those reactors are made for commercial purposes, not for scientific purposes, which means the experimenters don't have control over the reactor itself. You can't tell them, turn it off because I want to see what happens when it's turned off, for example, or reduce the number. You get what you get, which is what they're making to distribute power in China or in France. This shows how they complement each other. So what I've shown here in the upper left is the probability that you start with a certain kind of neutrino and it stays as that kind of neutrino versus length in kilometers as you go away from the reactor, 1 kilometer, 2 kilometers, 3 kilometers. And with what we know about the neutrino parameters so far, we expect the oscillation to change the number with distance. So just like going from the sun to us, start with a certain number, it gets reduced by the time you go a couple kilometers. If you go further, it comes back a certain kind of neutrino, like an electron neutrino. So that basically is the idea. If I look at these different neutrino experiments, you'll see they cover different spaces. That's just how close they are to the reactor. So the one that's the closest is in here, and the one that's furthest away is Daya Bay, the Chinese one. It can be further away and still do the physics because the reactors are more powerful and the detectors more powerful. So they were able to put it further away. Other features of these is just basically the power. Shows Daya Bay is the biggest, and how big the groups are that do this, which is typically showing you that we're starting, even though we're talking about neutrinos, not on an accelerator, there's several hundred experimenters that are involved, say at Daya Bay. It's a big, complicated experiment. I'll show you a little bit of that. This is a picture of the reactors themselves at Daya Bay. So that's what a fission reactor looks like. if you could go inside and look at one. Not very complicated. Now I'm taking the formula for how these neutrinos mix with each other that I developed for you quickly 2 lectures ago, or maybe it was last lecture, I can't remember. And if I take that formula and draw as a function of how far I go away from a reactor, this is the shape that you expect, and these are the different possible experiments. The Daya Bay one has a detector that's fairly close, one that's further away. Future detector is going to work here, and a detector that I'm going to show you in Japan is way out there. So the combination of those gives us the ability to measure these parameters well enough to draw these lines and distinguish which are the right lines. And this requires very high statistics. That's running a long time with powerful reactors, a very good scheme for getting rid of backgrounds, and a lot of what's very difficult in experimental physics, that's controlling what we call systematics. Things that change just because the temperature changes or it sits there a long time, or there are certain other reasons that things aren't stable or that you don't know them. This is a picture from the sky of Daya Bay. So here we have the detectors, and they have pairs of detectors here, a pair here, and because this is further away from the reactors, they have 4 up here, and the reactors themselves are down here. So they have a whole set of detectors. The detectors themselves are identical, and they just let the reactors go, and that's how they get their data. The detectors themselves, this is a picture of them. They're what we call gadolinium doped liquid scintillator. What that means is that they have what we call scintillator. Scintillator is something that if a charged particle goes through, it ionizes it, and the particular material picked decays in a way that gives visible light, or light, that you can detect in a photodetector. And they put gadolinium in, that's GD, because that creates a delayed signal that comes from the fact that neutrons interact with gadolinium and give a particular signature that they can see. And this makes it all work well. So that's the experiments. And with that, they can select unambiguous signals for the events that they look at. In order to get enough data, they run a long time. So they've run that, when I drew this picture, 1,958 days. That's something like 6 years. And so the data is taken over 6 years, and they have to be able to basically keep things stable enough to be able to compare data that's taken 6 years ago with data that's taken now. And they have controlled backgrounds in this difficult experiment down at the level of a couple percent, which is pretty impressive for something as rare and strange as neutrinos. So this is just, I'm just including these in your slides so anyone who wants to look. They use all kinds of different radioactive materials to measure the response of the detector, for example, as a function of energy. So these are all different radioactive ways to calibrate, and they get a curve that shows for 5 MeV how big a signal they get compared to 1 MeV, and so forth. They've done all this kind of very precise calibrations and experimentation to understand how to do this. Over a period of 6 years, electronics develops very quickly, and so you'll see the word up here, old electronics. What they've done in a way that's as non-interfering as possible is integrate improved electronics, computers, and so forth in a continuing collection of data. Then they build detailed models of exactly what the response is, and then take different radioactive sources to compare and do this very accurately. All this is done so that you can take finally data that you know that what we call the systematics or the non-controlled effects that just are in the data at a level that's small enough that you can see small effects, like these oscillation effects. So you want to make the systematics controlled over this complex apparatus, controlled to a few percent or a fraction of a percent over 6 years, which is a hard task, but they've worked hard to do that. And these pictures are just their tests and their monitoring to make that very well done. Then they get a result finally. So the result they have is shown here. This is oscillations. It goes down and it comes up, and you can see the error bars on it. So this is a fantastically improved measurement of oscillations compared to what we could do from the sun or something else. And with that, they then can measure these parameters in the formula that I gave when I developed the formulas, which are determined quite accurately. So for example, this is a key angle that we developed, sine squared 2 theta 1 3. This angle is crucial if we ever want to have the ability to use neutrinos to measure what we call CP violation. It's not anything I've talked about today, but it's our belief that it is a possible mechanism that's needed to explain why we have a matter-dominated universe. This thing has to be finite. So one result that came out of this is it's 0.08. It's not a big number, but it's not zero. You can see the error is much smaller than that. This made the physics community quite happy. It's just a parameter. But if that parameter, which we couldn't predict in advance, had been too small, then the future, not this experiment, but the future where we might be able to see whether there's a mirror asymmetry for neutrinos is right or not right. So it turned out nature has enabled us to plan in the future to be able to check whether there's what we call CP violation. And the difference in mass, which is this difference in mass between these neutrinos, is shown here. It's 2.5, 10 to the minus 3 eV squared. This is the best measurements that have ever been done, and they're consistent with the other experiments. I'm going to skip some things. We should take a break. Let me see where I can. Okay, now is as good a time as any, and we'll take a break and I'll skip a little bit of detail. But they'll be in the slides if anybody wants to see that. So we'll take a break and then continue.